So the last speaker for this session is Alexander Lev, and this is one of the distinguished papers of POPL 2023. So congratulations to Alexander and all the co-authors. And Alexander will tell us more about how to do automatic differentiation for probabilistic programs.
Great, thank you, Ning Ning. And hi, everyone. My name is Alex Lev, and today I'm going to be presenting some joint work with Mathieu Huot, as well as his advisor, Sam Staton at Oxford, and my advisor, Vikash Mansinghka at MIT, on a new program transformation for automatically computing the derivatives of expected values of probabilistic programs. So as we've heard several times in this session, automatic differentiation refers to a suite of techniques that can be used to transform programs representing functions into other programs representing the derivatives of those functions. So a typical AD user has some objective function, L, that they want to minimize or maximize, which they write a program T to encode. And then using the transformed program S, the user can then evaluate derivatives, which can be plugged into hill climbing optimization algorithms like gradient descent. Now, AD is one of the big success stories for PL thinking in machine learning. Tools like TensorFlow and PyTorch and JAX that we heard about earlier have transformed the practice of machine learning research, removing the need to derive and implement gradient computations by hand. But a curious thing is that some machine learning papers are still presenting hand-derived gradient algorithms, which raises the question, why don't they just use AD? And the answer, in many cases, is that their objective functions that they want to optimize are not traditional functional programs that you can just run AD on. They're defined as expected values of probabilistic processes. So what do I mean by that? Well, it's a pretty common scenario in machine learning that we have a program that's stochastic in some way, taking in a parameter theta and sampling a different random value x every time we run it, where what we're interested in is for each theta, the average or expected x value across all possible simulations. And we often want to find a theta that minimizes or maximizes this expected value. Now, the picture sometimes looks like this, with minimally noisy samples around the true value. But the same math applies across all sorts of qualitatively different situations. So, for example, the program that generates these samples has a stochastic branch in it, which is why when you look at a single theta, you get a kind of bimodal output distribution. Right? And if you look at it more, even though the samples look like they're getting higher as we increase theta, the proportion of the samples that are in the high branch gets lower as we increase theta, which is why the solid blue curve, which shows the expected value, actually starts to dip as theta gets too high. Right? So this need to optimize these expected values arises in all sorts of applications. For example, in decision theoretic applications, where our program might use the parameters of theta to simulate some process, and then evaluate a utility function in the simulated situation. So every time we run the program on an input theta, we're actually getting a different estimate of the expected utility for choosing that parameter theta. For example, in robotics, theta might be the parameters of an algorithm controlling a robot's arm. And our program might be simulating grasp attempts in a stochastic environment. And on each run, we're going to measure the grasp error, and we're interested in finding the theta that minimizes the expected error across all simulations. A very different example comes from Bayesian inference, where theta parameterizes a generative model, P, or an approximate posterior Q. And I won't go into all the details on this slide, except to say that just like before, the objective function that practitioners usually want to optimize, which in this case is called the elbow, arises as the expected value of a particular probabilistic process. And if you've heard of variational autoencoders or seen examples of neurally guided inference in structured probabilistic programs, those applications are all based on some kind of variational optimization. And this need to differentiate expected values arises in some other settings too, like reinforcement learning and sensitivity analysis that we have pointers to in our paper. The point for today is that in these settings, in order to optimize the objective function, we want to compute the derivative of the objective function at arbitrary points theta. But computing this derivative is usually not tractable. We don't even have a closed form program for the blue curve itself that we want the derivative of. What we can often do is estimate the derivative. So we can write a second program that every time you run it on some argument theta, you get a different slope, which I'm showing here in red. And the key property that we want this estimator to satisfy is unbiasedness. The average value of all the red slopes should be exactly the green slope. That is exactly the derivative of the average value of the blue probabilistic program. And those papers that I flashed on the screen earlier were designing and proving the unbiasedness of these red estimators for their applications. And what we're doing in this work is looking at whether we can automate the construction of these unbiased estimators. So just like an ordinary AD, the algorithm that I'm going to show you is going to accept as input a program that the user has written. But this time, its type is R to PR, indicating that it will probabilistically sample a real return value every time we run it. The objective function L the user cares about maps a parameter theta to an expected return value of running T on theta. And to perform optimization, we want the derivative of this function L. And what our algorithm is going to do is it's going to produce a new probabilistic program S of the same type of T as T, whose expected value is the derivative of L. Okay. The upshot is that just like an ordinary AD, after encoding their objective function as a program, the user won't need to do any more math by hand. They can automatically get this program S that can be directly run to generate unbiased derivative estimates for stochastic optimization. Now, this algorithm is the main contribution of our work, and we've implemented it in Haskell, building on popular existing libraries for probabilistic programming and deterministic AD. But beyond the algorithm, I'll just put in a quick pointer to our paper if you're interested in seeing our compositional correctness proof and how that works, how we handle programs that actually define and compose multiple expected values by including expectation as a first-class operator in the language, how we handle how we use some lightweight static analysis techniques in order to enforce regularity conditions that we need for our algorithm to be correct, and additional examples beyond what I'll show in the talk of recovering gradient estimators from the literature. But in the rest of this talk, I'm going to focus on giving some intuition for this algorithm and for the key technical challenges that arise when you try to differentiate probabilistic programs. So the first key challenge, which is well known in the machine learning community, is that it's not clear how we should be propagating derivative information through probabilistic primitives. And to explain what I mean, let me very quickly review, for maybe the third time this session, how derivative information is propagated by standard forward mode AD. So remember that the main idea in forward mode is to replace all the real numbers that are flowing through our program with dual numbers, storing both a value x and its derivative with respect to some external parameter theta. For each primitive in our language, like sine or plus or times, we create a dual number version of the primitive, which propagates derivative information using the chain rule. So for example, if I apply sine to a value x and the derivative dx d theta, I get out both the value sine of x and the updated derivative, cosine x times dx d theta. And this is just the chain rule. It applies also to multivariate functions. If we know the derivatives of our inputs with respect to theta, we can get the derivative of our output with respect to theta. Once we have a correct dual number primitive for every primitive in our language, it's not hard to get a correct dual number program. We just update the type annotations to swap real numbers for pairs of reals. We change all the primitives to their dual number versions. And we pair any constant real numbers, like 3 in the last expression here, with 0 to represent that they're constant. They don't depend on theta at all. The translated program correctly propagates dual numbers, which means that if we pull out just the dual component of its return value, we get the derivative that we were looking for of the original program. Okay, what goes wrong in the probabilistic setting? So consider this probabilistic program here. It takes as input a number theta, and it uses theta to decide it's going to flip a coin. So theta is the probability of heads for this coin. And then based on the coin flip, it's either going to return 0 or theta over 2. And so if you look at what this looks like visually, it's a cleaner version of the example from a few slides ago. And as you can see from this picture, if we want to maximize the expected return value, there's a trade-off to make. Because increasing theta increases the reward in this else branch, but it also decreases the probability of going into the else branch in the first place, right? And if we analytically compute the expected value and its derivative, we can see that the best choice of theta is 1/2. Now, if we apply AD naively and try to just replace all the real numbers with dual numbers like we do for a deterministic program, and all the primitives with dual number versions, the first problem we run into is that this flip operation is a primitive, so it should have a dual number version, but it's not clear how such a thing could be implemented. In order to be compatible with the rest of the translated program, the type of flip's dual number version should be the same as the original flip's type, except that all the real values have been replaced with dual numbers. So flip's new type should take in a dual number representing both the probability p of heads and dp d theta, right, where theta is the external parameter. But the return type doesn't have any continuous values flowing through it. So it's just still a probability distribution over Booleans. And this should worry us a little bit because the actual meaning of flip, its behavior, depends continuously on the input parameter p. So we really should be propagating some kind of derivative information. But the only thing this spec lets us do, the only thing this type lets us do, is return a Boolean to the program. And it's not clear how to propagate that derivative information through a Boolean. And so in practice, a lot of existing systems don't try to propagate derivative information. If you are writing a program that you're going to apply AD to, and in the middle of your code you flip a coin, they're just going to ignore the derivative information, flip the coin, and give you back the Boolean. In our example, though, this would lead to a derivative estimator that ignores the dependence of b on theta and just differentiates each branch of our program. And this estimates the wrong derivative. Okay? Its expected value is not the derivative of the expected value of the original program. And this is not just off by a little bit. If we actually were to use stochastic gradient descent using estimates from this derivative estimator, it would tell us that the maximum value for theta is 1. But that's actually a minimum of this function. Okay, so that's the first key challenge. How do we propagate derivative information through probabilistic primitives? Now, the second key challenge is that our correctness specification that I set out at the beginning of unbiasedness is actually quite loose. There's not just one right answer to what the right derivative estimator is for a probabilistic program. For example, one way of fixing the flawed derivative from before is to keep the control flow the same, but to add correction terms in certain paths. And as a result of these corrections, the expected return value is now the true derivative. But it would also satisfy our spec just to deterministically return the true derivative, which in this case happens to be tractable. And in practice, there's actually a whole zoo of techniques scattered across literatures from different fields that practitioners rely on to develop good estimators for their particular objective functions. Practitioners choose which estimators to use based on all sorts of problem-specific factors, like what their time budget is, or how much variance they're willing to tolerate. Some techniques have restrictions that mean they can only be applied to certain objective functions. And you might also think about the ease of implementation when you're deciding what estimator to implement. Now, hopefully, automation is going to help us remove this ease of implementation factor from consideration. But these other trade-offs, in order to create automation that's actually usable for real problems that practitioners face, we're either going to have to somehow automatically strike reasonable trade-offs, or give users knobs that let them tell us where they want to be on this variance versus speed axis. And we need to make sure that we can express useful gradient estimators that people actually want to use. So those are the key challenges. Now let me give some intuition for how we addressed them. Let's talk about the first challenge first. How do we even propagate derivatives through random primitives? And the key problem that we ran into, remember, was that probabilistic primitives like flip don't seem to admit a correct dual number implementation because this type is too restrictive. How can you track a derivative just by sampling a Boolean? And if we zoom out, we can see a bit more clearly what's gone wrong. The original AD algorithm took all the continuous values flowing through our program and replaced them with pairs of continuous values to track derivative information. But when we added a probability monad to our language, R is no longer the only type that can continuously depend on a parameter, right? Probability distributions can also depend continuously on parameters, even if they're probability distributions over discrete types, right? So we really should be transforming not just the real values flowing through our program, but also these probabilistic computations. But what should we transform them into? And what ADEV does is that we replace the probability monad P with a particular continuation monad that will let probability distributions propagate derivatives. Now, I'm going to unpack what this particular choice means and why it's a good idea in a second. But I want to point out that because we're consistently translating this monad P into this other monad, our whole program transformation is going to look just as simple as it did before. We don't have to do anything special to handle the monadic syntax do and return. It's just that now we have updated to a more complex monad type that is going to let flip, for example, propagate derivative information correctly. So what's going on with this new type? What's the intuition here? Well, an interesting perspective that comes both from measure theory and from a long line of work in probabilistic programming semantics is that we can view a probability distribution P as a higher order function, mapping inputs F to their expected values on samples drawn from P. That is, we can think of a probability distribution over X as a function of type X to R to R. And I'm being slightly imprecise here because this expectation can fail to exist, so the codomain should really have some kind of lifted real numbers, but for now I just want to convey the intuition. And an important aspect of that intuition is that this representation of a probability distribution is not lossy. If two distributions have the same expectation for every function f, then they really are the same probability distribution. Okay? Now, the nice thing about using this representation of a probability distribution is that its type is something we already know how to propagate derivatives through. We just replace every input and output type with dual number versions. And I'm using this notation D to mean dual number translation of. So if X has any real numbers flowing through it, this DX is also going to replace all of those with dual real numbers. Okay? Now, if we use this representation of probability distributions, which leads to this type for the dual number version of a probability distribution, what would that mean? Well, for any distribution P, we would need to produce a higher order dual number version, P sub D, that accepts as input a procedure f theta in dual number form, and is able to compute the dual number containing both the expected value of f and its derivative. And if you think about this for a minute, imagining P to be a normal distribution or P to be some complex distribution that a probabilistic program implements, you'll realize that this is totally intractable. There's no way that we can implement PD because it would require exactly computing an expectation and exactly computing the expectation's derivative. So our second insight is that we can just relax this specification. We can take the type that we got from just thinking of probability distributions as higher order functions, but say that instead of having to implement the dual number thing perfectly, you can instead just return unbiased estimates of the dual numbers that the original thing would expect. So everywhere where we were using deterministic dual numbers before, we're now going to use, in the return values, we're now going to use distributions over dual numbers. Okay? And that type that I had on the slide is exactly this continuation monad that I was showing before, the one that we mentioned earlier. But I still haven't showed you how we actually implement, for example, a dual number version of a primitive that satisfies this spec. So if we go back to the problem of defining a derivative for flip, or a dual number version of flip, we have quite a different spec now. Like before, we're still receiving a dual number version of P, the probability of heads, that also tracks its derivative information. But now we also take in this second argument, this estimator, f tilde. And when we give f tilde a Boolean, the idea is that it's going to give us a randomly sampled dual number that's estimating the expected value of some function f and that expected value's derivative with respect to theta. And the reason that f might depend on theta, even though its input is a Boolean, is because in a higher order language, it might have closed over theta or something that depended on theta, right? This f is just a higher order function that might be also depending continuously on theta. And our job in our implementation of flip is to use that estimator for f to produce an estimator of f's expected value with respect to flip and of the derivative of that expected value. Now, it turns out that this specification admits lots of correct implementations, not just one. For example, we could use the fact that the expectation of flip is just a weighted sum. And so what we could do is we could say, I'm going to sample once from f of true, call f of false, and then compute the weighted sum and propagate derivatives like I know how to do. But this calls f twice. We can get away with calling f once if we use the sort of reinforced technique from the literature, where we sample a random b, we call f on the sampled value, and then we compute this correction term here. And this technique is frequently used because it's so cheap and widely applicable, but it's also bad a lot of the time. It has very high variance. For a continuous distribution like normal, we can use the popular technique of reparametrization, where we sample a value epsilon from a standard normal distribution, then transform it smoothly before calling f. And note that all of these representations of these techniques from the literature are just a few lines in this representation. But the fact that there are so many correct implementations for each primitive is a reflection of our second key challenge, that there's no single right way to differentiate a probabilistic program. So how should we, among these various implementations, and there are many more that I didn't show, how should we implement each primitive in our language in a way that strikes the right trade-offs between variance, speed, and generality? And our answer is that we're going to implement all of them and inform users of the trade-offs. So we have lots of versions of flip and lots of versions of normal. And for correctness constraints, like the fact that a sample from normal reparam should only be used differentiably, we use our type system to enforce those correctness constraints. Now, the cool thing about doing things this way is that the user can rapidly explore a huge space of possible estimators just by changing which versions of different primitives they use in their programs. So if you have a program that samples 5 Booleans, for example, maybe depending on the previous results, you could choose to use the reinforce estimator at every flip, which yields an estimator that follows the same control flow as the original program, flipping a coin once per variable. If you really care about eliminating variance, you could get an exact derivative by using flip enum at each call site to explore an exponential number of program paths. You could mix and match reinforce any enum to reduce variance somewhat without incurring too high a computational cost. But you could also use weirder estimators, like this measure value derivative estimator, where when we actually use it at every sample site in our program, what ends up happening is we consider a primary program path, shown in blue, as well as all of the edit distance 1 program paths that come from just flipping one of the Booleans, okay? And interestingly, in our framework, this arises just by composing these measure value derivatives, but it's been previously discovered in the operations research literature where they call it the phantom estimator. Each of these what-if branches is a phantom path. Okay? We've also been talking in the last couple weeks to the authors of a paper that appeared concurrently with ours at NeurIPS about differentiating probabilistic programs, about how to take their novel estimator and incorporate it into our framework. And if you compose their version of flip using our composition rules, you get something that's kind of like the phantom estimator, but it only considers some of the phantom paths. Ordinarily, if you were working by hand, trying out all of these estimators would mean totally re-architecting your code. But for us, it comes out of just changing some primitives in your program. And one way to think about what's going on is that this is just forward mode AD, which is usually operator overloading, but we've also overloaded semicolon because we're doing this monad translation, which is what allows changing some primitives around to create such a variety of different control flows. In our appendix, we show how this architecture admits a lot of extensions to cover many gradient estimation strategies in the literature. One cool thing is that you can even include higher order primitives that have special sort of, special ways of computing gradients that are only appropriate for certain computations, right, parameterized by other computations. And this will have lower variance than if you were to just differentiate the internal code of a particle filter, right? So let me conclude by recapping what we've done and outlining our next steps. In this talk, we've presented a natural extension of forward mode AD to handle expressive probabilistic programs. Using ADEV, users can automate away the thorny, error-prone task of constructing and implementing unbiased derivative estimators for each new objective function, extending the benefits of AD to a broader class of important programs. And ADEV's modular architecture means that users can easily experiment with a variety of derivative estimators just by changing primitives in their programs to explore different trade-offs in terms of variance and speed. Researchers could also benefit from this modular architecture, using it to more rapidly explore the space of possible estimators. So we're excited about potential applications of ADEV and various directions of extending it that we'd love to talk about after this session. Thanks.
Thank you. We have time for a couple of questions, and we have a question over there. Please state your name and affiliation before asking the question.
Hi, Benjamin Kaminsky, Saarland University. You say on the what's next thing that you have programs that almost surely terminate, but the translation, so the automatic differentiation of the program doesn't. Do you have any insight why that happens?
Yeah, so that's a great question. One sort of simple example is if I have a geometric distribution or something like that that's constructed out of flips, right? So I'm going to keep flipping coins with some probability until I get tails. Most of the estimators are going to be fine with that. But if you use flippy-num at every flip, right? If you use flippy-num as the flip in that program, then the estimator that you're telling it to implement enumerates all program paths. And that doesn't hold, right? Because there are infinitely many possible program paths through the geometric distribution. So we have a conjecture that if a translation almost surely hearts, it's correct. We don't know whether that's true. And it would also be nice to just think more clearly about this. Our paper sets up a logical relations framework for thinking about the correctness of this algorithm. And maybe we could incorporate some results about the semantics of recursive higher order probabilistic programs into that framework to reason more clearly about these questions.
Cool. Thank you.
Let's take one more question.
Okay. Hello, I'm David Broman from KDH. Very interesting work, by the way. I was interested, do you support all kinds of distributions, or are there certain distributions that are more challenging, like multinomial or Dirichlet or something?
Yeah, thanks. So I'm not aware of restrictions on sort of what distributions could be added as primitives. You basically need to be able to come up with some estimator that satisfies this spec. There are limitations of the language. So like many differentiable programming languages, if I have a parameter theta and I am working with theta in my program and I do something like check if x is less than theta, we're not going to allow that. And our type system is going to prevent you from introducing discontinuities with respect to theta, even though the expected value of the program may still be differentiable in that case. You know, flip of theta could be written out as sample from a uniform then compare to theta, but we don't allow that. It has to be encapsulated in flip, which knows how to estimate derivatives. There is work by Jesse and others that looks at how to integrate certain classes of programs with integrals that have parametric discontinuities, and it would be interesting to think about whether ADEV could be extended in that direction.
Great. So in the interest of time, let's take the rest of discussion offline. So others will be around, so please reach out to them with questions and any kind of discussion. And let's give Alexandra and all the speakers in this session another round of applause.
Thank you.
Thank you, everyone.